Hi everyone. In this video we're going to talk about a very important concept, and we're going to also continue talking about limits. We're going to talk about continuity and one-sided limits. You can see the objectives that are listed here. We're going to talk about all of these different things, so let's get started. So what is continuity? Well, as you can see on this diagram, a continuous graph can be drawn without lifting your pencil. It's very predictable. So in this particular, you can see that as follow the ball around, if I can continue on in both directions infinitely, there are no jumps, no asymptotes, no holes. So that is a continuous function, and it's very predictable. So this illustrates what we said on the previous screen. It says that if a function f is continuous at x equals c at a point, it means that there is no interruption in the graph at c. And so you can see down here, you can see that you have a hole situation, right? So this is not continuous, a jump, and then a vertical asymptote. So this is the concept of a continuity, continuous continuity at a point. So as we continue to define limits and continuity, there exists this definition. This is huge. This is important. You must have this in your notes. This is what we are going to use. This is the litmus test that we're going to use to determine whether any function is continuous. It has to meet these three criteria. So for instance, limits and continuity. A function y equals f of x is continuous at x equals a at a point, right, at a particular place, if f of a is defined. Now, what that means is there is no hole, no holes. So that point has to exist, no holes. Also, there has to be, number two, the limit at that point, x equals a, right? The limit as x approaches a has to exist. So there's no hole, and it has to exist. Okay? So that means what? That means that you can have no asymptote. Okay? That point has to exist. The third criteria for a continuous function is that the limit has to equal the defined point. So in other words, no jumps, right? So it says that here, this cannot be a hole. It has to actually exist. It cannot be an asymptote here, otherwise it's not continuous. And it can't be a jump. And all these things should be pretty self-explanatory. So otherwise, if it fails on 1, 2, or 3, it is a discontinuous function. It is not continuous at that point. Okay? So that is the official definition. This is huge. This is really important. Be sure you get this in your notes and embellish it. Write it the way you need to write it so that you can kind of understand what it means. If there's any part of this notation that you do not understand, you want to put a big question mark by it so that when I come around and talk to you tomorrow, you will, or today, whenever you're watching this, that you will be able to ask those questions. Now, this notation is saying that the limit as x approaches a of f of x exists if and only if both one-sided limits exist and are equal. Yeah, I don't know what that random c is. Let's ignore that. It says that the limit of x, as x approaches a of f of x equals this limit, then that means that the limit from the left has to equal the limit from the right. Right? So this is just our limit definition. This is not continuity. This is our limit definition said in notation. That the limit from the left, as x approaches from the left and x approaches from the right, they have to be the same or there is no limit. Now, continuity on an interval. A function is continuous on an open interval. Obviously, the opposite of open is closed. If it is continuous at every point on that interval. Okay, so here, once again, this is a review. Here are the three types, or here are at least two types of discontinuities. There's a removable discontinuity, a hole. It's called removable because the limit exists there. Then it's removable, a hole with a defined value, right? You can see that here. And so when it says that the limit from the left has to equal the limit from the right, that point, f of a, this point, may or may not exist. It doesn't have to exist to have a limit. Another type of discontinuity is called a non-removable discontinuity. And that would be like a jump, right here, like a jump, that the limit from the left does not equal the limit from the right, and f of a may or may not exist. Okay? Non-removable, another non-removable is where there is a vertical asymptote. And so you can see here, as x approaches a from the left, it goes, f of x goes to negative infinity. As it approaches from the right, f of x goes to positive infinity. The actual point at f, as x approaches a, f of a, does not exist. This other type of discontinuity, and we've gone over these and over these, so I hope that some of them are becoming more familiar. This is an oscillation. This is sine of 1 over x. The function at a does not exist, and the point f of a does not exist. What ends up happening here is that it begins to oscillate, and so that the limit from one side, limit to the other is not defined, so that the limit doesn't exist where it oscillates. Now the limit does exist here. Do you see that? All of these points, and it exists here as well. But when it's looking at specifically this point here where it's oscillating, it does not exist. So here's an example using the continuous function definition. We have a function, f of x is x squared minus 4. C is 2. So we're trying to determine if the function is continuous at C. So the first part of the definition asks, does f of C exist? Does it exist? And so we look at the function, and we see that f of 2 is equal to 4 minus 4, which is 0. So does it exist? Yes. The second thing we ask is the limit as x approaches c of f of x exist? And we look at that and we plug it in, and we get we find that the limit as x approaches 2 of x squared minus 4 is equal to 0. The third criteria is, does f of c equal the limit as x approaches c of f of x? In other words, are they the same? And yes, 0 equals 0. So therefore, x squared minus 4 is continuous at c. It meets all three criteria. So here is another example. This is a piecewise function that has 3 parts. You can see that it changes pieces where x is equal to 0, where x is equal to 1. It has 3 pieces. This is a line, horizontal line. This is a line with a negative slope. And this is a parabola that's shifted up 1. And the question is, if is f continuous at, and it should say c equals 1, or c equals 0 here. So the first thing we ask ourselves, is f of c defined? Is f of c defined? So I know that c is 0, so I need to see, does f of 0 exist? And I look up here, and yes, this is equal on the second one right here includes 0. So I know that 3 minus 0 is 3. So f of 0 is 3. And so check, it does exist. Now, the limit at that point has to exist. And so I know this is a piecewise function, and so a graph might be kind of helpful here. A graph might be a little bit helpful. All right, so I know that at x equals 0, I know that f of 0 is 3. So let me put that in, 2, 3. F of 0 is 3. That's a closed circle. But I also know that according to the piecewise function, it's going to be 2 clear up until it gets to 0. So the graph actually is going to have an open circle at 2 and go this way. Right? The other one was a negative slope line, so it goes down like that, sort of. All right, so right away, as you look at the graph, you can see that it is not continuous because there is a jump there. So in other words, this would have to be a 3 instead of a 2 to make that a continuous function here. So this part 2 fails. It fails on part 2. And if it fails part 2, you don't even have to check part 3. So this particular piecewise function is not continuous. Now, the intermediate value theorem is a theorem that talks about functions over a closed interval. Functions over a closed interval, which means that it doesn't go to negative infinity and positive infinity all the way to the right and to the left. It doesn't go all the way over here and here. You're just looking at a function between 2 points here. We're just looking at this function. And what we're saying is that a function that's continuous will always have a value between those 2 pieces, right? Doesn't that seem a little self-evident? Okay, and so that's what that looks like. And then it says, if f is continuous and over this interval, and f of a and f of b differ in sign, then the equation f of x equals 0 has at least one solution in the open interval a to b. So a lot of what this is saying is that if you had a 0, so here's like the thing here, and you had like this, and you have a 0 here. F of x on this side is going to be positive. F of x on this side of the 0 is going to be negative. And we're talking about the y values, right? So somewhere between those 2 y values, there will exist a 0. So a lot of times what you have to do, if you have an example, say for instance, f of x is x squared minus 4. And you want to see if there is a 0 on the interval from -1 to 5. All right? So using the intermediate value theorem, what I'm going to do is I'm going to find f of -1, and I'm really just looking at the sign to see if there's a sign change. And so I would have 1 minus 4, and that's going to be a negative number, right? And then at f of 5 is going to be 25 minus 4, and that's a positive number. So somewhere on this interval there is a 0. The IVT does not allow you to find the 0. It just tells you that it's going to exist there on that. Of course, you know, it's a quadratic, so we could find it pretty easily. But we do know that it is continuous. It's a quadratic, it's continuous, a polynomial, and that there is a 0 because there is a sign change. And we can actually extend that, and we'll do that in class. The last screen is just a limit joke. I love this joke. I'll let you read it, but I think it's funny. I hope you get it. So I hope you'll write down any questions that you have from this video, and I hope that you actually listen to this video, and I will see you in class.